Chapter 4, Section 411, how can I determine the product? So chapters 4, 5, and 9 kind of add up into a shape called a parabola. So there's a lot going on here, but long story short, shouldn't be doing that. Long story short, we're going to be taking what we did in chapter 1, where we had the area as a product and the area as a sum. And what we're going to do is we're going to turn it into this shape in chapters 4, 5, and 9. And you'll notice there's a couple of key points here. We have x-intercepts. We have this point at the very bottom, which is called the vertex, and then we also have a y-intercept. So there's some major things that we're going to be learning in the next several chapters. I know this looks a little bit like a mess, which is fine. So let me go ahead and just sort of clear all this out. And I want to show you what happens if you go and graph y equals x plus 8, x plus 5, and if you graph y equals x squared plus 13x plus 40. Keep in mind, if you remember back from chapter 1 where we have the area as a product, this x plus 5 times x plus 8 should equal the middle all added together. You can see x times x is x squared, 5x, 8x, 40. So there's our x squared. There's our 13x, and there's our 40. And again, x plus 5, x times 8. You can see these do equal each other. And again, I want to show you an indication of how they equal each other. So if I go into Desmos and if I graph y equals x plus 8, x plus 5, you can see I get this shape. It's known as a parabola. If I graph y equals x squared plus 13x plus 40, you can see I get the exact same shape. And that's really important to understand. These are the same equations written differently, but they both have the same value and the same shape. And again, it goes back to what we talked about in chapter 1, where the product equals the sum. These are equal to each other, and we can see a visual representation of that right here about how they're equal to each other. So you don't need to know how to do this if you're kind of looking at this overwhelmed. This is what we're going to be working on for the next several chapters. Again, I do want to point out a couple of things though. If I zoom out a little bit, you can see there's some major points. We have some x-intercepts there. We have a y-intercept here, and we have the vertex down at the bottom. The vertex is either going to be the highest or lowest point. So again, between chapters 4, 5, and 9, that's what we're going to be looking at, is how we get these points. In chapter 4 specifically, we're going to be looking at these x-intercepts, this negative 8, 0 and this negative 5, 0. We'll fill in the vertex and the y-intercept later in chapter 5, and then we'll do some more complicated things with the whole thing in chapter 9. So that's just a look as to where we're heading. I hope that makes sense. So it says review what you know about products and sums represented by rectangular area models. We've already talked about this briefly. It says examine the algebra tile rectangle write an equation showing the area as a product and as a sum. I just want to assure you that it will be way less complicated. We won't be dealing with y's and all that stuff, but you can see this side is going to be x plus 4, and this side is going to be y x plus 2, so we'll call this y plus x plus 2. So that's the product, right? That's the product. Product means multiply, and that's going to equal adding it together, or the sum, and that is 1xy plus 1x squared plus 1, 2, 3, 4 y's plus 1, 2, 3, 4, 5, 6 x's plus 1, 2, 3, 4, 5, 6, 7, 8. So that's our product and as our sum. And then it says use algebra tiles to break this shape up. Quite frankly, I don't really want to use the algebra tiles to do it. I'm just going to do a quick area model. Again, if you'll remember, we did these back in chapter 1. So this is a 3x plus 2, so this would be 18x squared. Let me pause and make this bigger, sorry. Had a room there. But anyway, 6x times 3x would be 18x squared. 3x times negative 1 is negative 3x. 6x times 2 is 12x. Negative 1 times 2 is negative 2. If I want to write this as a product, I can say 6x minus 1 times 3x plus 2. And if I want to write this as a sum, nothing will add up to 18x squared, but these will combine and give me 9x minus 2. So hopefully we remember that. So that's problem 4.1. I'm going to clean this up and do 4.2. Changing a sum to a product is called factoring. When an expression is written as a product, it is said to be in factored form. And each of the expressions being multiplied is called a factor. So can every expression be factored? That is, can you rewrite every sum as a product? So again, when we do the area model, we're going from a product, right? We're going from the product to the sum, where we're multiplying, and we're going to go to the sum. When we factor, we're going to go the other way. We're going to go from the addition to the multiplication. So it's quite a bit more difficult. And what it's going to ask us to do is saying investigate the question by using algebra tiles to build rectangles for the following expressions. For each expression, write the equation that showing that the area as a sum equals the area as a product. If you cannot build a rectangle, be prepared to convince the class that no rectangle exists. So long story short, if we're going to do these, we would have algebra tiles, and you have to make either a square or a rectangle. If you can't make a square or rectangle, it doesn't count. If you can make a square or rectangle, it can. I'm going to pause the video and look through here because I want to find one example where we can make it a rectangle and one example where we can't, just to sort of show what we're talking about. Factor. You can see we turn this into a rectangle. I have 2x plus 3 on the top. I have x plus 2 on the side. You can see I have 1, 2 x squareds. I have 1, 2, 3, 4, 5, 6, 7 x's. And I have 1, 2, 3, 4, 5, 6, 1. So this would factor. If I were to take it from the sum, I can write it as a product like this. However, this one, I'm going to try and show you what I'm talking about here. I can't. Here's my x squared. If I have 4x on the side, right, there's nowhere I can put this one last one to make it a rectangle. So what if instead of doing 4 on the side, what if I go 3 on the side and go 1 down here? So there's my 4x's. Well, you can see I would need three more to finish, but I only have 1, so that wouldn't work either. And my final thing I could try is, what if I went a 2 by 2? I already tried a 4 by 0, it didn't work. I tried a 3 by 1, it didn't work. So what if I try a 2 by 2? You can see I would still need 3 more. So this one isn't going to factor at all. And we'll talk about the implications of both of these. But again, chapter 4, what we're going to do is we're going to work on strategies where we start with the sum and we turn it into the product. In chapter 1, we started with the product and we turned it into the sum, and it's pretty easy because we can use area models. But in chapter 2, it's a little, I'm sorry, in chapter 4, it's a little bit more difficult to go from the sum to the product. And again, I don't expect you to know how to do it right now. We're just talking about what's coming down the road. So hopefully that makes sense. So work with your team to write the sum of the product for following area models. Are there any special strategies you discovered that can help you determine the dimensions of the rectangle? So long story short, they've broken this up for us. They're not always going to break this up for us, but what we're doing is we're looking for what's the biggest number that we could take out of a 2x and a 5. I think 1's the biggest number that comes out of there. But what's the biggest number that comes out of a 6 and a 15? I think 3 is. And how about 2x's and 1x? I think 1x would be it. Now if we go down to the bottom, what's the biggest number between a 2 and a 6? Is a 2, and 1x and 2x's is 1x is the most. And here between 5 and 15, x, the biggest thing we can take out is a 5. Now if we look, 3x squared, 2x, 15x, 5. Having said this, I know that some of you guys, just from years of having taught this stuff, some of you guys see this instantly. You know what just happened. We worked backwards here, and you guys are totally comfortable with them working backwards. I know over the years a lot of you guys aren't going to be comfortable with what just happened right there at all, and I don't want you to worry about it. Again, chapter 1 is like, I'm sorry, 4.1.1, this section is like an introduction of what we're going to be doing throughout the whole chapter, and I'll be showing you guys some shortcuts and strategies and stuff that you can use, but this is sort of where we're headed. Again, we start with the sum and we work back to the product. So if I look here, what's the biggest number I can take out of a 2 and a 5? It's a 1, but should it be a positive or a negative? I don't know. Let's make it be a positive and see how that works. What's the biggest thing I can take out of a y and an xy? It looks like a y. Now we'll go down here. again, I have that positive negative thing, so I don't even know. We'll just make this positive again and see what happens, but I'll take out a 3. Now if I go to the sides, what's the biggest thing I can take out of a 2 and a 6? It's obviously a 2, but you can see that's going to need to be a negative, right? A negative times a positive is negative, a negative times a positive is negative. I still might have to, honestly, I haven't done this problem yet, so I still might have to go back and change these signs, but this is what I'm going with for right now. Now, between a 5 and a 15, the biggest thing I can take out is a 5, and an x and an x, the biggest thing I can take out is an x. So if we look here, I have negative 2 times 1y, negative 2 times 3, 5x times 1y, and 5x times 3. So if I were to write this, I could say 5x minus 2 times y plus 3 is equal to 5xy minus 2y plus 15x minus 6. Again, this is known as factoring, and we're going to spend a lot of time on this, so I don't want you freaking out right now if you're not quite seeing it, but what I do want you to see is how we take the sum and turn it into a product. We're working backwards. All right, same thing here. I guess since taking the negative out on this top worked, I'll make this a positive, so I can take out a 3x. Here I'll make this a positive, I can take out a 4. On the side, I will now take out a negative 3. And on the side, I will take out a positive 4x. So I get negative 9x, negative 12, positive 12x squared, positive 16x. So if I wanted to rewrite this, 4x minus 3 times 3x plus 4 is equal to 12x squared plus 7x minus 12. I don't want to get too deep into this conversation, but I will say the book did us a favor by telling us what numbers to put here and what numbers to put here. Actually, these two numbers would have been pretty easy, but these two, if I need to add this to 17, I could have used 3 and 14, I could have used 16 and 1, right? So why did we use 2 and 15? How did the book know to use 2 and 15? Same thing here. The 12x squared and the negative 12, they set themselves up, but if I want to add up to get 7x's right here, why use 16 minus 9? Why didn't they use 4 and 3? So those answers are going to be, those questions are going to be answered later on, but I do want to point out the last several years you guys have been doing these diamond problems in your homework and you don't know why you've been doing them. Well, all of a sudden we're going to be using those diamond problems to help us later in this chapter. So again, I know I'm just sort of throwing this out here, but it'll become a problem later, and I hope it makes sense that I'm just answering a future question. So it says, while you're working on problem 4.3, Casey noticed a pattern with the diagonals. It's pretty slick. 2x times 15x is 30x squared. 6x squared times 5 equals 30x squared. So is that always the case? If we multiply the diagonals, are they always going to be equal? And if we do it correctly, the answer is yes. So here, 2 times 15x is 30x squared. Guess what 6x squared times 5 is? It's also 30x squared. Here, I get negative 30xy. Here, I get negative 30xy. Here, I get negative 144x squared. Here I get negative 144x squared. So, long story short, you can actually use area models to factor. It's not my favorite way to do it, so I showed you here. If you picked it up, and maybe I'll show you 1 or 2 other times, I doubt it, but maybe you can use that method. I prefer to show the diamond. I have a 5-step process for chapter 4. I add 3 steps to it in chapter 5, and I think that's just the easiest way to do it, so that's probably how I'm going to teach it. Anyways, again, introductory chapter, just the idea, again, that these things we looked at in chapter 1 are equal to each other and they make the same shape, and that shape is known as a parabola. And we'll be working with the shape in chapters 4, 5, and 9. That's really the only thing you needed to get out of this entire lesson.